Welcome to Technical Founders. My name is Carlos Lara, AI Technical Founder, and today we will learn about CNN training and evaluation with PyTorch. Today we are going to continue from the previous tutorials, and the first one was defining our neural network architecture in a Python class, and the next one was preparing our data to be fed as input into our model. So now we finally come to training. So the first thing we need to do here is define our loss function. So as we know, we do gradient descent. We're going to do back propagation. So to calculate the loss, so we need a loss function. And in this case, because we're training a network to predict facial key points, so it's for facial key point detection, detect certain key points in an image, such as the location of the eyes, the mouth, and so on. This is a regression problem because our network is going to output X and Y coordinates for these facial key points on the image. So we need a loss function that is appropriate for regression. Now, in image classification with PyTorch, we used a classification. It was a classification problem, and we used a loss function that was appropriate, such as categorical cross-entropy loss. But here, because it's regression, we're going to use, in this case, mean squared error loss. And you can also use L1 or smooth L1 loss. There's a few options. So here we're going to import torch.optim as optim, so the optimizers. And first we define our criterion. That's how we define it, our loss function coming from NN, neural network, in PyTorch. And the next is we're going to define our optimizer, our gradient descent optimizer. So here we call optim, and we're going to use Atom. And Atom is just very nice. It contains momentum, and other optimizations are built into Atom, adaptive learning rate, and other things. So feel free to look towards data science or other documentation on Atom. But it's really good, and it's hard to go wrong with it. This can be a good default choice here when you're developing here using in PyTorch. So as parameters here, you're going to pass in the network parameters. So before we initialize our network as net, so it's an object, so net.parameters, so we can access them like that. So that's the first parameter of the Atom optimizer. And then we have a learning rate. And here for learning rate, we're just going to initialize it to 0.001. And again, Atom is going to, it does an adaptive learning rate. So very nice. So we have our loss function, we have our gradient descent optimizer, and now we are going to define a function that will train our network. So here we define a function. It's called trainNet, and we're just keeping it simple here in this tutorial just to show you how it works. But here it's only taking one parameter, which is the number of epochs. And this is not just a parameter, it is a hyperparameter. Hyperparameters are tunable. Parameters are in a way arbitrary, meaning you can choose what they are. You can select, you can tune them. So for example, you can change the values. You can train your network, and if it doesn't perform as you expect, you can change hyperparameters such as the number of epochs or others that we'll learn throughout the series. So here we have a number of epochs. And first, to prepare the network for training, we put it in training mode, and we just call the train on the network. So net.train method here. And then we're just going to define here a loss over time. You'll see in a moment why. We want to track the loss over time as the network trains. Pretty standard. And now here, so for each epoch in the range of epochs, so we pass in as a parameter the number of epochs, let's say 10, and then for epoch in the range of epochs, so this loop is going to run 10 times. So we're going to loop through the whole training data 10 times in the case of 10 epochs, for example. And in the previous tutorial, we covered preparing the data, loading it, batching it, creating the batches using our loaders with PyTorch. So here we're going to enumerate our train loader. So we have a test loader and a train loader. So it's where we loaded our batches using our batch size, which batch size is a hyperparameter as well that you can tune. So for the batch here index and the data, here's because enumerating here, when you do enumerate on the train loader, you give it an enumeration index here to each data entry. So we have our batch I, our index for that particular one, and then our data. So here we're going to pull out the images and the key points from our data. So data, we just grab the image, and then from data we grab the key points. And feel free to check the other tutorials of this to make sure that all of this is consistent. So we grab our data here, image, associated facial key points in that image. Then we're going to flatten those key points to be prepared for input into our model. And now those key points and the images, we are going to convert them to a float tensor in PyTorch. So this is just how you convert variables. It's standard to convert variables here to floats for regression loss, for this kind of regression problem. So just turn it into a float because, again, it's a regression problem and the output is a continuous value here. So float, we turn them to torch.float tensor. Change the type, cast them, and now this is pretty standard. We'll also opt zero the parameter, the weight gradients here. So just do optimizer.zeroGrad. So zero the gradient here every time you're going to come in here for each batch. So okay. So again, we have all these epochs. We're gonna loop through all of the batches for each epoch. So each epoch go through all of the batches, all of the training data. So zero the gradients, the weights here, and then now we do our forward pass here. So we define a forward function here, and if you just say net, so the network, the object, and you pass in the images, it will automatically call that forward method in our class. So it's going to do the forward pass, and these are the outputs. Of our network. So those X and Y coordinates for the facial key points. And now the next step, we just calculate the loss. So we have a loss variable here and our criterion here that we define. So our mean squared error loss. We are just going to, as parameters, pass both of these values. So we're going to pass the output from our network, and then the key points, our data, our actual labels, you could say. So what we want to compare it to. So we compare the difference between what the network predicted and what it should have gotten, what we wanted it to give. So we calculate the loss like that. And then we call loss.backward, and that does the backward pass to calculate the gradients here. So this is doing the back propagation. And here, the next step is just called the optimizer, our gradient descent here optimizer, our atom optimizer, and just call step. So this does the actual gradient descent step and updates the weights here. So now we're going to, so for our running loss, we're going to append loss.item. So we define here actually a running loss, and we're just going to keep track of it. So we're going to grab loss.item. Item is just so it's converted to the appropriate type here. And then, so for every 10 batches, we want to print out some information here. And here you can see some examples as the network is training. And to save time, I already trained it here, and feel free to do this yourself. Pause here, take a look how this is working. But we're basically printing out what epoch we're at, what is the batch we're currently on, and what is the average loss here. And the average loss is just the running loss here divided by 10, so just the average loss per batch. And then for the loss over time, we just append our average loss here. And we'll see in a moment why we want that. So we just printed. So very nice. So we're going to go through that for all of our batches, and then for each epoch we're going to go through that. So as the network is training, the network is learning here using gradient descent and backpropagation and calculating this loss function, minimizing the loss function. It's learning what are the weights that minimize this loss function. So it's finding those ideal values for our weight tensors and our bias, of course. So here, so we defined our function here, train network, and here we just defined our hyperparameter here, our number of epochs. You can tune that, and then this line is not important here. This is what's important here. So our train net function, we pass a number of epochs, and then we assign that to a variable we call training loss, because our function is going to return the loss over time here. And feel free to pause here so you think about what's going on here. But basically, the loss over time is because we want to actually plot that loss over time. So when we return that, when the model is done training here, we have our training loss that came back, and we just want to plot it. So we see how the loss as the number of batches is increasing, what's happening to that loss, and it's normal here to see some oscillations, but on average it should actually be going down. And as you see here, it actually is going down. And if we have more epochs, you can see it, and changing other parameters, you can see that. So visualizing our data and our model, our training is very important. It gives us an indication whether we're on the right track or not. So I like to do that, and I recommend it. So as you can see here, we're just printing through all of these epochs. We did 10 epochs, and the loss on average is decreasing. So that's something that we want, that average loss to be decreasing as the epochs and go by. So that's it. So we have our network, and the network has learned the weights and the biases that minimize our loss function, that gets gets the best outputs to match what we wanted it to give. So once we have that, now we want to test it. So we want to test. So again, feel free to pause, look at what's going on. But here, we're just going to grab this function as before, and check out the previous tutorials for this. So we're basically going to pull in our data here, our test images, our test data, test images, test outputs, our facial key points, and then we just compare here. So what the network gives us, and what it should have given us. So green is the labels, the actual outputs, what the network should have given. And then the magenta color is what the network predicts here. So as you can see, it's not perfect. I mean, you can do more hyperparameter tuning. There's more things that you can do. But on average, you can see, like, in generally speaking, it's actually matching really, really well. So what does that tell us? And the previous tutorial before training, we saw that it wasn't really good. Like on average, it was calculating that it was the center of the images. So the weights hadn't been trained. So it didn't have a clue, so to speak, what were the key points. But now after training, now they're distributed more where they should be. And again, it's not perfect. The accuracy is not 100%, but you can improve this. And as you can see, on average, it's very nice, and it's amazing that a neural network is able to learn by itself how to find those facial key points. So it's very, very, very nice here. And once you found a model that you trained a model, you found that it found weights, and you're comfortable and you like your results here, you can actually save your model. So you can save your model to a directory here, give it a name, and then you can use from PyTorch. You can use torch.save, and you pass a state dictionary. So you save the state of your network, so net.state dictionary, and then you save it at the model directory plus model name. And you can actually be more sophisticated here, save a more complex dictionary, save more. But here, to keep it simple, we can save it, and now you can just load it. You can load this this network that you saved, the state dictionary, reinstantiate it, and use the state dictionary, and you can just go ahead and classify or calculate the facial key points for your images without having to retrain the model again and wait for the training process. It's already trained. So you'll be loading a pre-trained model that in this case you trained yourself. So thank you. I hope you liked it. If you have any questions, thoughts, comment below, and I will see you next time.